So this is a diagram of our complete setup. You can see the server 1 which is running CNDP based UPF, the server 2 which runs packet generator based on DPDK. Now an explanation of how CNDP actually works. So CNDP accelerates the cloud native based packet processing application by aiming to provide better performance than that of a standard network. The socket interfaces using an input output layer primarily built on AFXDP, an interface that delivers packets directly to the user space bypassing the kernel networking stack. So the flow is something like this. The packets are arrived at the XDP hook point at the kernel driver level, and the BPF redirect program redirects all the packets to the AFXDP socket. Also here at the XDP level, you can even use your custom eBPF program. Now the AFXDP socket uses the mempool membuf provided by the CNDP platform. It also uses XSKDave API and other functionalities to accelerate the packet processing by the application. The AFXDP CNDP interacts with logical L ports and uses the busy polling mode. Also in this we are using NUMA nodes that are used along with DTP feature. DTP works along with XDP offload feature in the NIC hardware to redirect GPU packets directly to the user space via the AFXDP sockets, and it also supports zero copy mode. So moving ahead, the second diagram is the complete setup of our server that runs only CNDP based UPF. You can see the 22 queues here created that start from QID 0 from control plane traffic. Now the kernel stack is getting bypassed, and now you can see the user space memory which is divided into two, each of which is connected to AFXDP socket. Now let's zoom into the whole queue setup. So you can see the RX and TX queue here, and both of which are connected to the AFXDP socket. Now the completion queue is basically storing frame descriptors that have been successfully transmitted, while the fill queue is storing the frame descriptors that are ready to get new packets. So let's go back to our diagram, and above this you can see how CNDP is integrated with the UPF. So this is the CNDP repository on GitHub, and so this basically is a CNDP cloud native data plane is a collection of user space libraries which help us to accelerate packet processing for cloud native application. It uses AFXDP to do so. First I'll be showing you the functions folder for the functions. You have to go inside lib and core folders, and here is a list of all the functions. You can see it here, right here. Some of the important ones are XSKDave, mempool, and you just can have a look at them. Next we will be looking at the important one of the important files that we have, and to do that just go inside examples, CNDP fwd, and fwd.json .json file. So this is one of the important files and which we are concerned with, so just have a look at it. Now the second GitHub repository, which is the UPF, omic UPF, and so this repository is also important, and the CNDP repository is integrated with this UPF repository. So now let's move over to the terminal. So this is our first server, and you have to go inside UPF and conf folder, and the first file which I will show you is this one, which is CNDP UPF one worker.json. Let's go inside it. So this file is basically it basically shows us how to integrate CNDP and UPF, and there can be more files like this. So let's look at it. So you can see the application we are running, the name is given as CNDP UPF. Now let's go down. You can see the name of the two sockets here right now, and the information we have about them. Let's move down. So this is the whole file, and you can also see the MEM information right over there. So now before we move ahead, let me give you a description of some basic things. So we are using ICE drivers for both our interfaces, and we have DDP enabled The DDP feature works along with the XDP offload feature in the NIC hardware. It basically redirects the GTPU packets directly to the user space via AF-XDP sockets. And the DDP profile can help in GTPU packet traffic steering to the required NIC hardware queues by using RSS, which is the receive side scaling. So for this deployment, we are using Numa nodes, and we have two of them. Let me just show you. So you can see the one currently we are using is the node 0, and you can see both of the nodes here. Now let's look at some information about the ICE driver. For that, we need to run the mod info ICE command. This basically provides information about our driver, and let's now look at the huge pages information. For that, you need to run this command. So you can see the size of the huge pages here right now. Now moving ahead, we need to make a few changes in files, but before that, please remember that before this deployment, you have to turn the Intel IOMMU on, and you have to keep it on during this deployment. So now let's go inside the scripts folder. Inside this, we have to now modify our Docker files. So the first file is the docker setup.sh file. So the first thing you need to do, you need to change change the mode to CNDP right here. This file only has one change. Now we have to go back to the conf folder, and now we will go inside the docker inside the upf.json file, sorry. And once you are inside it, again the mode should be CNDP. You can see it's here right now. And another thing you need to do is you need to provide the path to the CNDP UPF worker file, which is right here. So you need to do this before you move ahead. So finally, we are set to run a make docker build command. This should be run from the UPF repository itself. I already have done this, so I won't be running it again, but you will have to run this docker build command. So just run this. And another thing I have to mention right now is that we are using a single worker thread for packet receiving part, even though we have 80 cores, but this is only for simple testing and to see the performance of a single worker. In our future videos, we will increase the worker for better performance, but let's see what a single worker thread can do. So let's look at our containers, docker ps. You can see them. I already ran this before. So right, so now let me show you logs, docker logs. So you can see the worker sockets, they are working fine. Let's move ahead. Just run your commands to see if everything is fine and in working order. Now we can see the now it's time to see the best logs. So these are the logs for best. Right, so So this will launch the best daemon in the foreground, and it will set up, and this basically helps us run the gRPC API server, and it will call the best.cc file to select the worker and socket assigned to it. The CNDP initialization will start by passing the CNDP UPF1 worker.json file, which we have shown you before, and this will now create a UMEM of size 32768 MB, that is CNDP memory pool creation, and initialization will be started. So now the XSK socket will be used, and everything will be done in busy poll mode. So both are successfully deployed and integrated, and now let us move to the second server, which is the DPDK based traffic generator. So I'm inside the second server right now, and for the traffic generator, first we need to bind the interfaces with VFIO PCI, and to look at the interfaces with VFIO PCI, you have to run this command, bind. So here you can have a look over here. Right, so let's move ahead. So the next thing is you need to run the docker run command inside the UPF folder itself, and I already have done this, so I won't be doing you again, but I'll surely be showing you the command. So please run this command before you move ahead. Now after this, for the packet generator, we have used 4 worker threads to generate more packets. Now to generate the packets, you need to run this command. Again, I have already run this command, so I won't be doing it again. So after that, you can use this command. So now you can see the speed of the traffic generation, speed at which the traffic generation is taking place, and you can see it's around 21,000 Mbps approximately, and on the left side you see Mbps, which is basically million packets per second. Okay, so let's move ahead. So now what we need to do is we need to go inside the BSD container. For that I need the container ID. So let's move inside the best container. So now let's move inside the best container. So for that I need the ID, docker ps. You can see this is the ID. So docker so we are inside the best container. Now you have to run this command before you move ahead with ctl, but before that please make sure that port.py and best.py file is present inside the container. Right, so once we're here now, we can have a look and have a look at some basic stuff and information that it provides us with. So first of all, let's do this to look at the port. Show port. You can see all the information comes up here right now, the packets, and next we can monitor port. So here you can see the number of packets dropped, the speed, mbps, and etc, etc. So let's move ahead to show the traffic control. Should you see, here it is. Now let's monitor this. So you can see again mbps and mbps right here. All right, let's move ahead. So the status of our workers right here. And now let's run this command to have overall look. So you can see the active worker threads, the available drivers and plugins. All the information is right here. So now the packages have been generated, and let's check out our deployment in the lab. So this is our SUT system under test. You can see we have two servers over here. Both of them are running on 80 cores and have 128 GB of RAM. The NIC that they are using is E810 Columbia series, and the first server is running CNDP based UPF, while our second server is running traffic generator, which is based on DPDK. So you can see these two servers are connected, and we have used SFP modules to connect them. And the first interface is the access interface, and we also have the core interface over which the packets are being exchanged. So now let us go back to the server 1 to check the benchmarking speed and the UPF throughput. So this is the complete data plane graph. You can see the complete pipeline. On the right hand side, you can see the rate of packets being transferred in Mbps, that is million parts per second, not Mbps. Now we will see the total packets arriving, and you can see the total packets arriving in the UPF and being processed by BES. You can see the various interfaces there, and you can have a look at the fast BPF, IP checksums, link merge. Also at the PDR lookup, it currently fails because we have not applied any PDR and FAR rules, but we can easily resolve them by applying them. So you can see the whole pipeline here and the whole structure. So after we have applied the PDR and FAR rules, we can again look at the graph, and the PDR lookup section, which was earlier giving us errors, we can now see that that error is gone. You can see the PDR lookup section once again, and this error resolves itself once we have applied the PDR and FAR rules. So now we are inside the server 1, and right now we are inside the BES container, and let's look at some information about our packets. So the first is show ports. You can see the CNDP port here, and you can see the packets, and it is also given in bytes. And now you can just have a look at the monitor ports, which will basically show you the speed. And again you can see the speed, which is approximately 3.6 Gbps, and this is only using a single worker, so you can assume the steep increase in throughput on increasing the workers. And now we will monitor the traffic control. Before that, let's look at the traffic control, and you can see there is only one worker. Now on monitoring the traffic control, again you can see the speed, no packets are being dropped. Also the speed here is given in Mbps, also in Mbps. Mbps is basically million packets per seconds. Okay, so now let's move ahead. So again you can see there is only one worker running, and to clear any confusion, we are using the 6 number core, not 6 cores. Okay, let's now look at the all the information, and that is basically the ports. And now we will be finding the CNDP port. You can see the active worker threads, which is worker 0, and now we will find the CNDP port, and this CNDP port shows over here that it has been successfully integrated. So now let's look at this image. So we used AF packet mode basically, which is the normal mode before this to deploy, and you can see the speed here. It comes around 270 packets per second, and now you can just observe the enormous increase in throughput which CNDP provides. And we have only used one worker here, and imagine the performance when you have multiple workers. And in our future videos we will try to use multiple workers. Thank you.